Okay, I want to go over some fundamental assumptions about horizontally launched projectiles with you. So we can imagine the cannon is at a height above the horizontal. The distance from the cannon to the ground is your displacement in the y. Something that we remember is that the x and the y are independent of one another in projectile motion. So what happens in the y is it is accelerating as it goes down. That acceleration in the y is going to be constant, and that's going to be little g. If you're measuring from a frame of reference from the top to where it lands on the bottom, the displacement is a negative value. If you're looking up to find the height of where the cannon is, from the Earth, you're having a positive displacement value. Remember that acceleration in the y being little g is always going to be a negative 9.8 meters per second squared because it's moving downward. One thing that we need to keep in mind is here the projectile is at its maximum height, or the y max. At that point, with the horizontally launched projectiles and even angle launched projectiles, your velocity in the y is going to be equal to 0 meters per second. Let's talk about a few of the assumptions of the x value. So x is the horizontal. So from the point where the cannon is shot to where it lands is the displacement in the x. Another word we use for that is range. And let's make some assumptions about the acceleration. First, we need to point out that there's equal distance intervals of the motion in the horizontal direction. So even though there could be acceleration constantly pointing down, there's actually no acceleration going in the horizontal direction. So the initial velocity in the x is equal to the final velocity in the x. So therefore, acceleration in the x is constant, or 0 meters per second constant. There is no change per second squared, excuse me. So there is no change of acceleration in the x. There is, however, a velocity value. There's a magnitude to this velocity as it's shot out. The initial velocity in the x is equal to the launch velocity. So it is launched in this direction horizontally. So the initial velocity in the x is the velocity that it is launched with. And sometimes we refer to the launch velocity as v naught. Okay, because velocities are vectors, you know that they get split up into x and y components pretty easily. So along its path, the velocity in the x is constant. The size of the arrow and the direction indicates that it's staying horizontally with its velocity, but also that the magnitude of its velocity is constant. There is no change if we were to draw those vector arrows. And if we were to draw, let's get a different color here. If we were to draw velocity in the y, it might start out with very little velocity, but as it goes down, that velocity in the y increases. Until it hits the ground here, where it's going to land and stop. The x and the y are independent of one another. You want to break things down into two columns. so that you can keep track of all your variables. There's going to be given variables, measured variables, and then assumed variables. In the case of our experiment, we don't know what the displacement is going to be horizontally. This is our target, basically. We're trying to hit the cup, right? So we don't know what that's going to be. But I'm doing this in the lab, and I have a table that I can measure. So I can know my displacement in the y. I know from the top of the table to the floor, it's going to be a negative 0.76 meters because I measured that. Initial velocity in the x, as we said, is going to be our launch velocity. At what speed does the ball leave the table with, right? So what I had to do was a couple of different trials to get this. And I got an average of 1.042 meters per second. So what I did was I constructed a ramp here to give the ball some acceleration. Then I allowed it to travel flatly along the table. And I'm going to take this distance, the delta x here, and I use the stopwatch to measure the time, right? And as it went around, I kind of got a couple of different trials there. I was getting half a meter for my distance, and I was getting about, 4.45 seconds, you know, 0.58 seconds, et cetera. And so I took the average of those times. And since we know velocity is displacement over time, we can take the average of those values and divide them. And your meters are always going to be the same, but your times might be slightly different. And for me, I got 1.042 meters per second. So that's where I got that from. So really, this thing is going to be an experiment in two parts. You need to find or calculate an average velocity to make this happen, because that's going to be very consistent for you if you keep using the same setup. So using that value, we're going to actually plug it into one of the kinematics equations to find the displacement. Another assumption we're going to make, though, is that since there's a constant velocity in the horizontal, that means there's no acceleration in the horizontal, so that value is 0. So basically, I'm almost there. Do I know my velocity in the y? I have to make an assumption on that. So my initial velocity in the y, since it just starts going at the very top at its maximum height, it's going to be 0 meters per second. So that's an assumption I'm going to make. Acceleration-wise, I know that gravity is the culprit. So acceleration in the y is going to be little g. That's going to be a negative 9.8 meters per second squared. And that's constant. So here we have constant acceleration. We can use our kinematics equation when you have cases of constant acceleration. Beautiful. And one of the kinematics equations that we're going to use is going to help us find the bridge. What is the bridge? If we remember, time is the bridge, okay? Time is the key. All of these are independent of one another. X and Y, they're independent of one another. In order to cross over between X and Y, we need a key or a bridge, right? So there's a couple of ways you can use this one kinematics equation. Let's find a nice color here. How about green, light green? All right, so we remember that you have a displacement is equal to the initial velocity times the time plus 1/2 the acceleration times the time squared. What's cool about that is you get to check all these boxes off. You can use this for the x direction or the y direction. So using this in the x, Using this in the x direction, we're going to call it delta x, is initial velocity in the x times time plus 1/2 the acceleration times time squared. So our values here that we can plug in, do we have displacement? No, that's what we're trying to find. Do we have an initial velocity? Yes, we measured it. Do we have a time? No. Do we have an acceleration? Yup. And we don't have a time. So this is incomplete for us to use in this class because there's two missing variables, and we want to find a way to solve this with only one missing variable. So let's take a look at the y side. All right, so delta y is the initial velocity in the y times time plus 1/2 acceleration times time squared. Oops. And we want to look at what we know, what we have. Do we have displacement in the y? Yeah, that was actually the height of the table to the ground. Do we have initial velocity in the y? Yeah, because we're assuming that that's 0 meters per second. We don't have time, but that's okay because we're looking for time. And do we have acceleration? It's due to gravity, right? So we can use that. So the two missing pieces of our puzzle here are going to be time. All right, let's see if we can break this down even further. I want to start canceling some of these values out and make it simpler for us. We have delta y, and I want to plug that value in. The delta y was 0.76 meters. We measured that. That's the height of the table. And my initial velocity was 0 meters per second. And the time was unknown, plus 1/2 of little g. It's negative 9.8 meters per second squared. And times time squared. All right, cool. What can we do here? Well, 0 times time it will allow us to basically cancel that part of the equation out. So it's going to become delta y is equal to 1/2 acceleration times time squared. So let's do that. Let's follow up. So 0.76 meters is now 1/2. Sorry, I should say negative because of that displacement being downward. 1/2 of negative 9.8 meters per second squared times time squared. All right, so I can get rid of all these things by dividing it on both sides and taking the square root. So what does that actually mean? Can we simplify this formula even further? So on the top, you'd have displacement. Underneath that, you'd have 1/2 of acceleration, and that's going to equal t squared. Well, how do you get rid of a square? You square root, right? So then our formula becomes even simpler. Our formula becomes to find time. You take the square root of the displacement divided by 1/2 of the acceleration. So next time that you use this, it's going to be a lot simpler for you because you have that shortcut built in. So let's continue this. So 0.76, negative 0.76 divided by 1/2 of negative 9.8 gives us this big decimal, and it's like 0.1551. Oh, I think that's a 6 if I read my handwriting correctly. 62041 seconds squared. That equals time squared. So let's take the square root of both of those, and I get another long decimal. I get that time is equal to 0.3938299965. Let's simplify that one a little bit. Let's say the time is about 0.40 seconds. All right. All right, so now I have my key, my bridge. It's 0.4 seconds for my time. Beautiful. What can I do with that information? I can plug it back in. to, let's scroll up with the arrow. I can plug it back in to find my displacement. So now on my x side, I can find this unknown that the delta x is equal to my initial velocity in the x, which was 1.042 meters per second times my time of 0.4 seconds. And there's actually no acceleration, is there, guys, in the x. It is a constant velocity. So that, my friends, is not going to be used. We're going to cancel that half of it, right? So next time you use this horizontally, you could say that the displacement in the x is equal to the initial velocity in the x times time. So plugging that into your calculator, you get a displacement of 0.41370,823 meters. Let's simplify that. Let's say it's about 0.41 meters. And that is where I want to put my cup. So I set up as a ramp with a horizontal portion of a run, basically. The ball's going to start up here. Gravity's going to make it roll down here. It's going to maintain its constant velocity. And it's going to go off the table down a distance, which is the displacement in the y, and it's going to land somewhere here in the cup. So this is my range. It's predicted to be 0.41 meters, right? And that's how you do it.